Not many of us have the back strength to carry a whole lab's worth of equipment on our backs. Digilent makes USB scopes that are tiny, you can fit in your pocket, but there's the Analog Discovery 3 and the Analog Discovery Pro. So what's the difference? I chatted to Arthur to find out, and he even gave me a demo of 2 of the Analog Discovery units in action. If you want to check out the specs for the Analog Discovery Pro ADP2230, head to ipXchange.tech/DigilentADP. Hey, it's Eamon with ipXchange, and we've got an excellent ipXchange tutorial for you today. It's the first time we've had the hardware, the software, and the interviewer all in frame, so this is going to be a great edit. If you haven't seen any of our previous chats with Arthur, Arthur is an applications and support engineer at Digilent, so he's the perfect person to talk to when you want to demonstrate a product. And in this case, we're talking about Digilent's Analog Discovery series. So the Analog Discovery series are these compact USB scopes that you can easily plug and play and get measurements for low voltage applications. So this is perfect for embedded applications and audio applications. And somehow Arthur has managed to get both of those niches into 2 demos for us. So without further ado, here's what I learned when I chatted to Arthur from Digilent about the Analog Discovery series. I've heard the Analog Discovery series be described as kind of a lab in your pocket. So it's not just an oscilloscope, right? There's a lot of other tools in there as well. So
Yep. Yeah, power supplies, digital I/O. So in this case, like for the demo I've set up, I'm running like full on 8 digital I/O pins out to a board that we're looking at, and then also capturing some audio data through an adapter. So it's like, it's not just straight like oscilloscope probes or test leads or anything like that. There's also like all sorts of different adapters and things you can connect up to it, get all sorts of different analog inputs and outputs going. Both digital and analog data, power supplies, a whole bunch of different interpreters for different kinds of data. So like for different protocols like UART or SPI or I2C, both like reading and writing. It's really, I don't know, say something like 13 different instruments in the box, and like in a box that really is like that small.
nice. You've also got an Analog Discovery Pro series, is that correct? So
Yep.
what's kind of, actually I think I can see it there. So what's the difference between the Analog Discovery 3 and the new Analog Discovery Pro or ADP2230?
Yep. So we have a couple different like families inside of the Analog Discovery Pro line. So there's the 2230 is kind of the entry level one. It's around double the price of an 83. Has similar capabilities, but it's like professional really is in the name. It is intended for professionals. So like rather than like a relatively limited but still extremely useful like 32 kilosample scope input buffer on the 83, this thing can record like over a second of data at 100 megasample per second. It's like fully, like there's DDR memory inside that's capable of storing just a lot more stuff on the device so that you don't have to rely on like slowly recording data over USB.
Nice. And in terms of the people who would be using the Pro versus the 83, what are we talking? And what would you need such a big memory buffer for?
Yep. So it's really, we can see like pros and hobbyists and everyone like using an 83 anyway for just like quick and dirty measurements. You can do basically anything you want with it to start with. But like when you're trying to do like really more precise, repeatable tests that like need to like work the same way every time, capture a whole bunch of data, analyze all that data, that's where we really see the Pro coming in. Is it's set up just a lot better for like, you can make sure that there's just no gaps in your data. Like if you're trying to just get a look at like a signal that's coming in, and like having like, I don't know, just like you can picture like a sine wave or something like that coming in off of like a waveform generator. If you're capturing it on an 83, that smaller buffer, if that sine wave is really fast, again, 100 megahertz or a megahertz plus, let's say, then like as it comes in, it's going to get chopped up into chunks, and you're going to be missing small parts of it potentially.
Okay.
So really what that bigger buffer is for is to make sure that everything is absolutely continuous. You don't miss any detail on like a much longer test potentially.
Okay.
So it's, yeah.
These aren't just scopes, are they? You can interface them with other equipment. So if you wanted to say interface analog discovery unit with MATLAB or LabVIEW, what kind of applications can you see one of these devices being permanently installed rather than being kind of a carry around
Yeah.
lab in your pocket?
Right. So yeah, I mean, we have, like you'd mentioned, we have support for LabVIEW, MATLAB. There's a SDK for C, C++, Python,
Mhm.
um, other various kinds of control. Like there's support for like you. We have instructions on the web for getting it set up with like a Raspberry Pi as a host, like PC kind of
Okay.
thing as well. So it's like, yeah, you can picture, I don't know, like in a lab where you really need like a repeatable test for stuff
Mm.
coming off of a production line. Like you're trying to test like PCBs that are coming out of like just coming off the press, let's say. Um,
Okay.
then like you'd be able to have something set up like a custom like adapter board, let's say a test fixture that just like plugs into an 83, and then like you have your custom application set up with Waveforms SDK where you just like hit go and it runs your test, and like custom PCB could potentially do all sorts of stuff like switching different electrical paths so that you can check different test points, right? So like you might be able to use a digital IO as like a mux in that kind of situation as well. Multiplexer, just like picking different
Nice.
test points, applying different tests to a PCB, just like again, like at the press of a button. Like that kind of situation, it's usually more involved in setting stuff up just because it does require some programming, but
Mm.
that's also what LabVIEW and MATLAB are for.
Cool. So obviously there's a lot of measurement tools within the what was the name of the software? Is it Waveforms?
Waveforms
Wave,
SDK is the like the software layer, like programming
okay.
software. Yeah, it's
Okay.
Waveforms is like the application that runs on the
Okay.
computer and you interact with. But yeah, it's that software development kit. Is really what we're talking about there.
Cool. So if you were to say um, have an oscilloscope for timing and then let's say a frequency spectra,
Mm-hmm.
um, is there a way of automating measurement of, say, recognizing a certain frequency peak
Yep.
and okay, cool. So you can read
Yeah.
data off the measurement and automate processes in that kind
Yeah.
of situation.
Even like just in the app itself, without even getting into the SDK, there's a whole scripting
Okay.
engine built in, like a scripts instrument that lets you like do anything that like the software application can already do. So like FFTs are built in. There's a spectrum analyzer instrument.
Mhm.
Like you can already like go in and like find those peaks just in like scripted tests within the application itself, like the GUI.
Nice. And just to double check, this is because I know this the
Mm-hmm.
83. A lot of students like it. So
Yeah.
these are plug and play devices, aren't they? You can just take one out of the box
Yep.
and have a scope in front of you, effectively.
Yep. Yep. Software's installed. You just like plug it in, select it in the device manager, and it's pretty much good to go.
Nice. Um, so in terms of the physical connections on the 83 and
Mm-hmm.
the ADP 220 and the ADP2230,
Yeah.
what are we talking? Because I noticed that the Pro had some proper BNC connectors.
Yep. Yeah. So it's just starting with the 83. Like we have the test point leads. Like these are kind of the standard for
Mhm.
a lot of this kind of device. They do run into bandwidth limitations just because it is like a long cable that introduces capacitance. So
Yeah.
we have a BNC adapter for the 83 that like lets you break out to BNC scope probes and use those.
Okay.
Um, but it's a separate piece of equipment that you buy separately and then have to plug into the device. So when we went over to the Pro, we like understood that like that kind of bandwidth concern is really critical for professionals, and just being able to capture as high speed of a signal as you can is just super critical. So in this case, we just built the BNC connectors directly into the device itself. So I'm going to scroll probe here as well. Oop, I think that's coming through.
Oh, I see. Nice. And in terms of the construction,
Mm-hmm.
I guess the Pro is more ruggedized.
Yeah, aluminum case.
Cool. So just to double check, if
Mm-hmm.
someone is already using the AD3, is that the same kind of pinout as on the uh, ADP2230, or is it a different layout?
Um, so like thinking about the test lead specifically,
Yeah, yeah.
yeah, they do use different connectors and different things. That wire set comes with the device, so it's not
Okay,
something you need to like pick up separately or anything like that. So if um, AD3 adapters generally aren't compatible with the 2230. It is a question that we've seen
okay,
before, but it's yeah, it doesn't they don't quite play together. The main difference being that those scope pins just aren't connected to the MTE cable set on the
okay.
2230 itself. It's a little bit of different pinout.
But is this
Yeah,
the software the same?
software's totally the same.
Okay, cool. So if you already had like an automated workload on an AD3
Yep,
but wanted to port it over to the
yep.
ADP2230, then that's fine.
Yeah, you can just switch out the device and it should work. There's some small differences in terms of like frequencies that are achievable in firmware, but
Mhm.
it's all mostly handled under the hood in waveforms.
Cool. And other than that big buffer, are there any I/O differences
Hmm.
between the two devices?
The biggest one, so it's single AWG channel for the 2230 instead of two, which can be relevant.
Okay.
There are other Analog Discovery Pro devices that offer two channels of output. This one was just, we're trying to keep the costs down. Um,
Okay.
Others, yeah.
So if you did need two AWGs, you
Mm-hmm.
would still go with the 83.
Or we have like the Analog Discovery Pro 3250, one of the higher end
Okay.
devices. Yeah.
Okay. Cool.
Yeah.
Um,
The biggest other difference is USB 3 support. It's full USB C. Both devices are USB C, but the Pro
mhm.
has like full USB 3 speed. So you can,
Oh, cool.
when you're in, there's a couple different like streaming modes going on. So like when you're just running like normal repeated acquisitions, it like captures a buffer, stores it on the device, and then forwards it up fairly slowly. Uh, and then you have a record mode in the app as well that lets you lets you stream data back to the host over time or record into a buffer,
Okay.
right? So if the sample rate that you've set is low enough, typically under I don't know 5 megasample per second for the 83, then you can just
Mhm.
continuously record into your PC's RAM. So it's like
Okay.
you can just capture as much data as you want, but it only works at relatively low speed. For the 2230, because it's USB 3, that lower limit there, that upper limit in terms of streaming rate is quite a bit higher. It runs up to 10 plus megasample per second, like when you're doing a continuous recording like that.
Cool. So can you think of a particular application where you would need the USB 3 speed?
That gets more into stuff where you're using the SDK and just trying to
Okay.
consume a lot of data.
Okay.
Like you could theoretically, it's so you're limited when you're streaming like that. You are limited to like a 200 megasample buffer on the PC, just so we don't eat up all of your RAM.
Okay. Yeah,
But
yeah, yeah.
the yeah, you can see. Um, but like if you're in the SDK, you can theoretically do like a fully continuous kind of processing thing. So like having it
Okay.
sit there and record infinitely, process that data, and then do something with it, right? Whether that's like send a
Okay.
message if a particular event occurs, or yeah,
Nice. Uh, so I'd be very interested to see these devices
yep,
in action. So yeah, if you share your screen with this with the scope, and then if use your camera so we can see the equipment, then can you
Yep.
just explain what setup you've got on demo?
So starting out on camera, because on the camera here, just because it's a little easier to understand what's going on when you know what the hardware is. We have an Analog Discovery 3 here. It's connected to an audio adapter with audio cables running to a PMOD I2S2. This is just like a simple little ADC DAC device that is like converting data, pushing that into an FPGA. The FPGA is doing a little bit of processing of that data and then sending it back out. So we've effectively have like a full loop back here. So there's audio data running out of the 83, like through this whole setup, through the FPGA, back out. It's being recaptured by the 83 there. We also have like on the I2S interface between the FPGA and the PMOD, we are capturing the digital signals for that as well. Just like through this little test point header. So jumping over to waveforms now. We have the power supplies turned on. There's some amplification circuitry in the audio adapter that needs it. We're generating a couple different waves just through the WaveGen, and then we're recapturing here. So
can you just explain what are the three? I think it's three. What are the different kind of windows within waveforms that we're looking at?
Yeah, so on the bottom right is the power supplies. You can see down there that's just supplying power to the adapter.
And that's just left, from some of those pins.
Yeah. It's power supplies are typically the red and white ones here that I think you might be able to see.
Yeah,
camera's moving around a lot, but bottom left is WaveGen. So similarly, it's just another couple of those pins. In this case, routed out through the audio out connector on the adapter. In this case, we're just generating two different frequencies of sine wave. The view above this, let me zoom in, is our digital line. So let me pause that so we can actually take a look. So you can see yeah.
So that's the signals coming from the FPGA.
Yep. Yeah, this is just like a straight I2S interface. There's like the left-right, it's a left-right audio channel, like select pin, a serial clock, and then data coming in. And you can see it's being interpreted here as well, like decoded for you in waveforms.
Nice.
And then, so one of these channels is output, the other is input. You can kind of see that by the FPGA is fast enough that like between you could see like this sample was 571 here. And then just like on the next cycle, it's already being sent out of the FPGA. It's the same piece of data just flowing through.
Cool. And I guess the top one is the audio trace being read in.
Yep. That is the actual analog audio data from the connector. Plus an interpreted version of the signal that's going into the FPGA. So we are using that's not correct. There's WaveGen 1. So we're looking at the WaveGen output going into the PMOD, and then the analog output as well. So it's input, output. We can compare the two, see how they differ. In this case, there's just an
And just for my amusement, can we see that with a fast Fourier transform on it so we can see the frequency?
Yep.
Thank you.
So my favorite tool. Should see some spikes in here somewhere. Probably need to capture some more samples. Yeah, so now you can see a pretty good spike at 0.1 kHz. So that's 100 hertz wave coming in.
Nice, low. Cool. So in terms of setting that up, how easy was that to do?
20 minutes probably is honestly mostly just fiddling with hardware, trying to figure out like how to get all the connections wired up. Like the software is much easier to like get everything connected in.
Cool.
Yeah.
So if we were to switch over to the ADP2230, how would that look?
One more thing I want to show you in here just before we jump over to that is that just like for a comparison point. So I've been doing some zooming in and out here. The thing to notice with that is that that's automatically changing the sample rate. So like when I'm looking at something like relatively zoomed out like this with the analog data, we're actually only capturing at 160 kilohertz. Whereas like, so if I zoom in all the way, right, you can see that like we're still capturing digital data, but you don't have the resolution, you don't have the sample rate to actually be able to pick that up and like interpret all of the little bit flips.
I see.
When we compare to the Pro, we'll be able to see that like when we do a full recording, capturing into memory, we're going to be able to capture both at the same time.
Oh, cool. And in terms of the memory buffer, is that basically what we're seeing on the screen?
Yeah. So there's underlying memory underneath. So this is like a rendering, but like you can see everything. Like when I zoom out here, like that full contiguous like memory buffer is like left to right on the graph. Like,
okay, cool.
Yeah.
And just so we have a benchmark for when we switch over to the Pro, how big is that buffer?
I think we're running at 32K on this one. So there's some different configurations you can use for the 83. So you can bump up the amount of buffer that you're dedicating to scope, but it's 32K is the default.
Okay, cool. Nice.
It might be 16. Anyway. It's everything's shown in here as well, and you can limit the number of samples that are being recorded. So default here, and then we can bump it down to 8K or lower if we don't need that much data.
Okay.
I'm going to switch to hardware over to the Pro. This might take a second. Okay, so I am over on the Pro now. So This is kind of similar hardware setup. So in this case, I'm still using the 83 as like a signal source in this case, running from this cable over the input here, running the audio output over to a scope probe with a little breakout board. I don't know how visible that is.
Okay.
There.
Also, to clarify, the AD3 is still doing the signal, but the ADP2230 is doing the read-in.
Yes, exactly.
Okay, cool.
And read-in for both digital. So but a part of what I was talking about there was getting the digital lines just connected into the Pro instead of the 83.
Cool.
Cool. I'm going to jump back over to waveforms.
Nice.
So we are now looking at the Pro. So in this case, we have, again, we're just looking at the input. So digital and the digital on the bottom here, and then the analog data on top. In this case, we're looking at both. So it's not just analog data up there. There's the lighter orange is our analog scope channel one. And then the darker orange is data that has been interpreted from the digital line. So I have a map channel set up to do a quick little conversion from one of the digital interfaces here, and then plot that next to the analog input.
Cool. So what are all the little spikes?
Honestly, I'm not totally sure. It might be some interpretation noise or an issue with the FPGA. Like the firmware that's running in there could be like doing something slightly wrong. But we're seeing a fair amount of like there's a little bit of noise in the analog signal too. Like you can see it wobbling there a little bit. So like that could be affecting it to some degree.
So in terms of the data buffer, how much larger is this than the 83?
So in this case, we're looking at 1 million samples recorded. So it's
That was compared to 32K, was it?
Yeah, 32,000.
Wow.
So it's, in this case, it's like 300x, something, 30x.
Wow.
And the Pro goes a lot higher than that as well. Like this is a million samples. It can go up to 256 million total.
Mm-hmm.
So it's like you can go much, much higher even than just that. And to really kind of show that off, like we're looking at like, I don't know, 100 milliseconds something of data on screen here. Mm-hmm. And then we're able to zoom in, and you'll remember what I was saying with like being able to interpret the digital lines. We're able to fully zoom in and inspect every individual like I2S packet that's going on a, what is that? I mean, 10 megahertz sample rate. In this case, it can go up to 100 megahertz. I have it running a little bit slower to reduce the amount of data that we're capturing. But like 10 megahertz, we're looking at like 100. What even is that? Sorry. 100 nanoseconds, like spacing. Over.
Okay.
Yeah.
So in terms of what would you, what kind of things would you use that that level of speed for if you were, say, like recording a firmware dump or something?
Yeah. So like one example that we've had it showed up in a white paper that we put out a while back, is that you can like record the entire boot sequence of like of like a processor booting from flash, like every individual byte that it reads out of flash, like as it's like loading like its program, its application from memory. In that case, we were booting like a Zinc chip, and it was like, I think, I don't know, probably a couple hundred milliseconds of like SPI data, like running at maybe like 10 or 25 megahertz, like SPI clock, just capturing all of it.
And I guess there's no way you could do that with the AD3.
Yeah, you can capture it in small pieces. If you know what you're looking for, you can set some very specific triggers to try to find like what the bug is. But like when you're working with a small buffer, you really need to know what you're looking for in like a longer sequence like that, as opposed to just capturing everything and going back and searching for it later.
Nice. Is there anything else you wanted to show us on the Pro?
I think that was it for this. We could actually take a look at FFT again here as well.
Yeah.
Which, I mean, we're seeing all sorts of those spikes are showing up in here as well.
Yeah, very much so.
Yeah.
Well, that is a very strange spectra. Interested to know what's going on there, especially with the notches.
Mm-hmm.
What are those occurring at? What's the interval between those notches?
Like the dips.
Yeah.
Is that like 45-ish K?
What's the next one?
90 looks like.
Okay.
Somewhere between 84 and 95.
So, is there anything set at like 45K?
I wonder trying to remember what 48. It's the audio digitization frequency.
Oh, okay. So that will be it.
Standard 48 kilohertz. Yeah.
Oh, I see. It's funny, and we wouldn't have been able to see that on the 83, would we?
I don't think so. Yeah, again, because like we'd be looking at spectra of like just that 100 hertz, and we can't look at it at the same time because you just don't have the range.
Wow. Cool.
Sick find.
Yeah. So we've had a really good look at the 83 and the ADP2230, the Analog Discovery Pro. Arthur, if you could summarize 3 key points for each, what their advantages are, what would you say?
Yep. 83, it's low cost, super easy to use. Again, fits like fully in a pocket. You get a fair amount of the same stuff with the Pro, but like when it comes to like just pure ease of use, like even those MTE cables are like perfect for breadboarding. You can carry it around. Like you don't need to like handle separate BNC cables, all that kind of thing. The Pro really does all of the same stuff as the 83, but just adds more power. So higher bandwidth, higher sample rate, more precision, capture a lot more data. Exactly what we've been looking at over the course of this demo.
Cool. And I'm sure there'll be plenty more analog discoveries to come.
Yep.
So I look forward to chatting to you about them in the future.
Sure, totally.
And thank you thanks very much for giving us the demo.
Yep. Yeah, thank you for having me. This was really fun.
And to anyone watching, if you're interested in learning more about the Analog Discovery series, we've done a full write-up of the ADP2230 because we know you're a professional design engineer. And yeah, if you're interested in learning more about the technology after that, we can put you in touch with Digilent, and I'm sure they'll have plenty more to say.
Where my engineers at?